Okay, we're going to start looking at some properties of tangent lines to circles. So if you remember what a tangent line is, it's a line that basically touches the circle at one point, and it also has to be perpendicular to one of the radii of the circle. So you can see here, this black line intersects the circle C at some point. We can call this point D, and it makes a right angle with that radius. Same thing over here with this red one. If I make this red, same thing, meets circle C at some point of tangency. So the key thing is, if you want it to be tangent, it's not also at one point, but also has to make a 90 with the radius. So if you look at example 1 here, it says, is CE tangent to circle D? Now EC is this segment here. So if this is going to be tangent, then we know this has to be a right angle. So if that's true, then we would say triangle ECD is a right triangle because it has a 90-degree angle. So if it has a right angle, then we know the Pythagorean theorem must hold. So if this is true, then 11 squared plus 43 squared would have to equal 45 squared. Now 11 squared is 121. .43 squared is 1849, while 45 squared is going to be 2025. So if 121 plus 1849 equals 2025, then we're good. But this actually is 1970, and this is 2025. So these are not equal. So since those are not equal, that means angle E is not a right angle. So that can't be a right angle. So EC is not tangent. So it has to make that right angle. The Pythagorean theorem must work, and that's the easiest way to show that a segment or a line is tangent or not tangent to a circle. So once we know something is tangent, and more importantly, if we know two things are tangent, we have a very important theorem that we can use to work with tangents. So this theorem says if we have two segments from the same exterior point that are tangent to a circle, then they are congruent. So in this case, if we are saying if AB, line AB, and line DB, if those are tangent to circle C, then we can say, because they meet at this exterior point B, we can simply say segment AB, which is the point of tangency to the exterior point, is congruent to DB. They are the same length, they are the same segment. So we can say this is the same as this, if they're both tangent, and they of course have to meet. So we can use this theorem on a lot of different types of problems, but here is an example where we say AB and AD are both tangent to circle C. Find the value of x. Well, since these are both tangent, they meet at an exterior point, namely A, they're both tangent, then these segments are the same. They're congruent. So we would simply say 5x plus 5 equals 10x minus 3, because that's the value of those segments and they are equal. So I would distribute the 10 to solve this equation. So 5x plus 5 equals 10x minus 30. I would subtract 5x from both sides just to get the x on the same side. So that would give me 5. 10x minus 5x is 5x minus 30. I'll add 30 to both sides. which would make it 35 equals 5x, and then I'll simply divide out by 5. So 35 divided by 5 is 7, so x equals 7 in our case. Now, if we wanted to figure out and plug 7 in, we certainly could. We get 40 and 40, because 5 times 7 is 35 plus 5, which is 40. But just that simple. Alright, a couple new definitions that we have that kind of goes along with this idea of tangency is the idea of circumscribed and inscribed. So we say the circle is inscribed if each side of the polygon is tangent to the circle. So our inscribed one, which is this orange one down here, it's really important because every side of the polygon is tangent to the circle. So if I had a center here, this radius would be perpendicular, and this radius would be perpendicular, as with this one, as with this one, as with this one. The opposite would be a circumscribed polygon. A circle is circumscribed about the polygon if each vertex is on the circle. So you can see it's basically inside. So each vertex is on the circle. So we can really use this theorem to kind of help us do a lot of types of problems with these properties of tangents. So if we look at this one, it says find the length of each segment. And there's lots of segments here. The first thing I'm going to do is I notice I have lots of radii of circle C. So I see BC is 7, but since it's a radius, then CD would have to be 7. So would CE. So would CH. So would CG. All those segments would be 7. And since this is perpendicular, we know that this, and this is a diameter, we know these are going to be tangents. So we know AB and AE are tangent to circle C because they basically both have that 90 degree. So we know AB and AE will be the same length. So since AB is 24, AE is 24. But we already know part of AE. We already know FE is 9. So AF is going to be 15. And we just simply get that by 24 minus 9. So this value is the 24, which is the whole thing, so it has to be the same, minus the little segment of 9. So now the last segment we really have to find is AG, which is kind of this segment right here. So this one's probably the hardest one to see, but if I look at triangle ACE, I'll try to draw it over here. If I draw ACE over here, I have a right angle here. I know this side is 7. I know this side is 24. So using Pythagorean theorem, I can find what this side is. It is the hypotenuse, so we can say 7 squared plus 24 squared equals x squared, or c squared, or whatever you like. So this will help us basically find AC. So 7 squared is 49. 24 squared is 576 equals x squared. So if I add those together, I get 625 equals x squared. And so I will take the square root of both sides, which will leave me with 25. So AC is 25. But if you look at AC, which is this whole distance, we already know part of it, which is AG. So GC. So since I just want AG, I'll take 25 minus the 7. That will leave me with this little part is 18. Let's look at our last example. It says find the length of each segment. So what we are going to assume in this problem is we are going to assume that all the segments that appear to be tangent are tangent. In your homework it'll say kind of a similar statement. I did not write it on this, but we will assume all these are tangent. So the neat thing about all these being tangent, we basically have 3 tangent lines that are all the same. So what this says is we have 2 tangent lines that meet an exterior point, the tangents are the same. So if I think of this one segment, 6.4, I can label it. Let's say this is A, and this is B, and this is C. Since AB is 6.4, I would know that AC must be 6.4, because all tangent segments that meet at the outside of a circle must be the same. I can do a similar thing up here. Let's give this a letter. Let's call this D, and let's call this letter E. Well, since DB is 10, then the other tangent that meets at D would also have to be 10, which would be ED. So both of these blue segments are 10. So let's name one more letter. Let's call this letter G down here. Well, now we know DG is 19.8 because that was given in the problem. But DE, which basically goes, part of that is 10. So by subtraction, we know EG would be 9.8. And then since, again, these are both tangent, we would say GC is also 9.8. So you can see this part and this part are the same. Again, because these are all tangent. This part and this part are the same. Okay, so hopefully this is not too bad. If you have questions, please let us know about tangents.